Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 4.4, Determinants. So determinants are used in a lot of places. It can be used to find the cross product, which I have kind of demonstrated before, but I haven't actually explained. Now I'm gonna do that. It is also the scale factor of mapping, so after you map a certain diagram by, say, a certain vector, or matrix rather, you will get a certain magnification in area or volume, and that would also be the matrix determinant. You need to know something called the singular matrix, which has determinant 0 and it has a special property, and I'm gonna talk about those in the next video when we talk about the inverse of matrices. But for now, I'm gonna just leave single matrix as is and talk about determinants in general. So let's make up a matrix 2 by 2 for a start. Let's have a matrix A, B, C, D, the most general form. So it's kind of difficult to state what exactly this whole determinant is, but let's have a look. So in order to find said determinants, there are obviously ways of proving this. For now, I'm just going to show you what it is. What it is essentially, if you have a matrix in any dimension, if you multiply all the diagonals downwards from top left to bottom right, then subtract by all the diagonals from bottom left up to the top right, then you should be able to get the determinant. So this whole thing in a 2 by 2 ABCD would be AD minus BC, sort of basic, because it's just 2 by 2 in general. So let's try something different. Let's try a 3D matrix. I'm gonna start ABC, D, E, F, G, H, I. So what you really need to do here is to get all the different diagonals. There are 3 different diagonals down and 3 diagonals up. For the purpose of just me talking, down will be top left to bottom right, up will be bottom left to top right. Obviously you can do the arrow either way because it's multiplication, it's commutative and all those boring stuff, but it doesn't matter. This is the points that I want to demonstrate. So let's try finding this. So there are some diagonals that only have 2 terms, there are some that only have 1 term. To solve that, copy the whole matrix to the other side. Now we have 1 diagonal, 2 diagonals, 3 diagonals. And you realize that AEI is the same. It's repeated, which means that they're identical, so we don't take that into account. So we, in a nutshell, we only have whoops, that's bad drawing. This 3, not including the A. So we have this diagonal 3 by 3 kind of matrix thing that are diagonals that we need to add Similarly, we have a negative diagonal of CEG and all the way up to B. So we have essentially red take blue as our determinant. So let's try that. So if AEI plus BFG plus CDH. Then we take away CEG, take away AFH, take away BDI. This is the 3-dimension determinant. Now, the ones who were paying attention back when I was doing the cross product, I did use cross product in by way of finding the determinant of a 3x3 matrix kind of determinant, except the fact that I didn't use this exact method, because this method is actually kind of basic. It's not really that nice to use. It gets out of hand very fast, and it's just, in general, the more algebra you write, the more likely you're going to make a mistake. So instead, I'm going to use something else. Let's rewrite the anti-matrix DFGHI. So we have this 3x3 matrix. Rather than using this diagonal method, I'm gonna use the 2x2 determinant method, which is I will take the top row as a special case. I'll take the red A and the determinant of EFHI, so they are in diagonal. I will take A multiplied by the determinant denoted by DET of the matrix EFHI. So I've got this first term, then I let's see, let's go blue. Then we take away, this takeaway is important, by the way. Similarly B, except this time it's DG and FI. So note that if the lone term takes row 1 and column 1, then the matrix avoids those two rows and that row and that column. So for B, they avoided the first row and the second column, but they're still a 2x2. So we've got a B multiplied by a DET of matrix DFGI. And finally we have, let's use green, plus, sorry for the color blinds, yeah, this is green. So I've got C and DEGH. So if add C, that of DEGH. So we've got these three terms, we sum them up and we get the determinants. So the type determinants of A, B, C, D, E, F, G, H, I is equal to this whole thing. And we already know how to find the determinant of A, B, C, D in a 2x2 matrix, so you can just expand this whole thing and those algebras should add up to be the same, which will be a relief. I think for now, for determinants wise, I like this method a lot more because it's less likely that you're gonna get algebra errors by just multiplying a lot of diagonals, and it also saves you a lot of time, especially when you get to the point when you look at a 2 by 2 matrix and you can just churn out the determinants just by looking at the matrix. There are people who can just look at 2 by 2 matrices and just shout out a number, and that would be the determinants. You are not expected to get to that level. Anyway, so let's talk about this negative. This negative is special because it when you have this matrix thing, you are really not expected to know a lot in terms of how the matrix actually work. A more general form of dealing with matrices are called the suffix notation method, which you are not expected to know, nor will I teach you, because it's really quite either annoying or confusing to start learning. Once you get the hang of it, it gets really helpful, but for A-level purposes, not worth it. So there is something that you need to do to a matrix with a negative sign. So in general, you want a checkerboard pattern. So you want plus minus, etc., plus minus, etc., go down in diagonal, alternate pattern. It's essentially checkerboard of plus and minuses, and you also take like essentially you want the dimension. First dimension is just the plus, then 2 dimension is this square 2 by 2, 3D this 3 by 3, then etc., continually expanding as you go higher dimensions. For 3 by 3, your checkerboard matrix is as shown. This would be more relevant next video when we talk about the inverse matrix, but this also applies in our case of using this determinant method. So the B has a negative from this checkerboard thing, if you ever want to question where that actually comes from. For now, that has been said, determinant has been taught. Forgot to say there's also one more thing that you need to know about determinants, which is when you determinant a matrix M n, which is, again, we have talked about transformations in a kind of compound way. After transforming by matrix n, you transform by matrix M. Oh, by the way, when you do that, you need to double underline your matrices, just to separate from just simple algebra factors, which is single line, and matrices are double lines. So the determinant of the transformation M after n is essentially equal to the determinant of the matrix M multiplied by the determinant of matrix n. So it's kind of logical to think about this. So if I enlarged a certain thing by a factor of 2 by n, then determinant n is 2, because the determinant, as I have said, is the scale factor of a transformation. Then if I then multiply this determinant by a shrink factor of half, then I should get a half as your determinant, and that would result in 1. So Mn will have a determinant of 1, and you can check that as well. So if I have a, let's see, 2002 is a scale factor of 2, that's n, then I multiply m in front of it, which is half, 0, 0, half, then you should be able to get just 1, 0, 0, 1, which is the identity matrix. But that doesn't need to be the case, and the determinant happens to be 1 times 1 take 0, which is just 1. That equals 1. So yeah, it fits this whole thing, which although this is not a actual proof, this is something that you need to bear in mind, and it will save you time if you do take care. So when it comes to matrix questions, really practice is the only thing that matters. The more you do, the more likely you're gonna be able to grasp the mechanism of the entire matrix thing, and especially when dealing with the determinants of a 3x3 matrix, you do need to do a lot of it. You could challenge yourself doing a 4x4. It's essentially the same method as doing a 3x3, except the fact that now on top of the 3 let's see, so you have a 3x3, you have to do 3 lots of 2x2s. Now for 4x4 you need to do 4 lots of 3x3s, which each of the 3x3s are 3 lots of 2x2s. So it's as you scale up dimensions, the complexity exponentially increases. Not recommended at all, but if you have too much time, I guess you can have a try. So I've made these 2 questions for you today. Find the determinants of the following matrix. Yeah, you have 5 seconds to pause and do the questions, and I'll show you the answer in 5, 4, 3, 2, 1. And there we go. The answer is -1 and -29. So yeah, that wraps up the determinant video. I hope you've learned something. If you have any questions regarding matrix in general or just determinants, do let me know in the comment section below, and I will see you on my next one.